Ever wondered how PCA works in machine learning? Today, we dive into the fascinating world of principal component analysis, or PCA for short. This is a powerful tool in the realm of machine learning, widely used for its efficiency, simplicity, and interpretability. At its core, PCA is a dimensionality reduction technique. It simplifies the complexity of high-dimensional data while retaining trends and patterns. It does this by transforming the data into fewer dimensions, which can be easier to work with and visualize. What's more, PCA is a key player in tasks like noise filtering, where it helps to smooth out our data, and feature extraction and engineering, where it assists in identifying which information is most important. It's a versatile tool that can be applied in a variety of machine learning scenarios. Now that we have an understanding of what PCA is, it's time to delve a bit deeper and understand how it works. PCA functions by identifying the directions, or principal components, where the data varies the most. Now let's break down how it works, step by step. First, we start by centering the data around 0. This is crucial, as it eliminates any bias that could be caused by the location of the data. Next comes the calculation of the covariance matrix. This matrix measures the relationship between different variables in the dataset, essentially telling us how much one variable changes in relation to another. After this, we perform eigenvalue decomposition on the covariance matrix. This process translates our matrix into a set of eigenvectors and eigenvalues, which are fundamental in defining the orientation and magnitude of the data. Finally, we select the top k eigenvectors based on the eigenvalues. These eigenvectors form the new dimensions of our data, and voila, we have our principal components. So that's the basic run-through of PCA, but what if we want to speed up this process? Enter Randomized PCA. A randomized PCA, as the name suggests, introduces a random element to speed up the PCA process. Now you might be wondering, what's this random element? Well, it's an approximation technique that uses randomization to swiftly approximate the first few principal components. Yes, you heard it right. It's an approximation, not an exact calculation. But don't let that discourage you. This approximation is quite accurate and can save you a lot of time, especially when dealing with large data sets. In fact, randomized PCA can be significantly faster than regular PCA for such data. It's like taking a shortcut, but still ending up very close to your destination. The beauty of randomized PCA lies in its capacity to handle large volumes of data without compromising too much on accuracy. Randomized PCA can be a game changer for large data sets, but what if our data isn't linearly separable? That's where Kernel PCA comes into play. Kernel PCA extends the standard PCA technique to work with nonlinear data. Now you might be wondering what exactly that means. Well, let's break it down. In principal component analysis, we aim to find the directions or components where the variance of the data is maximized. However, this technique assumes the data to be linearly structured. But what if our data isn't linear? That's where Kernel PCA comes in. It uses a kernel function to map the original non-linear data into a higher dimensional space where it becomes linearly separable. In other words, it transforms the data into a space where we can apply the standard PCA. This essentially expands the use of PCA to a wider range of datasets, including those with complex non-linear structures. So if you're dealing with a dataset that doesn't quite fit the linear mold, don't despair. Kernel PCA can be a powerful tool for working with complex non-linear data. Today we've explored 3 variants of PCA: the standard PCA, randomized PCA, and kernel PCA. Let's quickly recap. PCA, or principal component analysis, is a statistical procedure that uses an orthogonal transformation to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables. Randomized PCA, on the other hand, is a fast approximation of PCA that uses a random projection to reduce the dimensionality of the data. Kernel PCA, last but not least, uses a kernel function to project data into a higher dimensional feature space where it becomes linearly separable. All these techniques serve unique purposes and have their own strengths, be it data compression, noise filtering, or uncovering complex data structures. Understanding these PCA techniques can provide you with powerful tools for analyzing and interpreting your data. So keep exploring, keep learning, and see where PCA can take you in your machine learning journey.